Okay, AP Chem students, this is Mrs. Pinkerton. Buckle your seatbelts because 1.3 elemental compositions of pure substances has a lot of information. And again, back from unit 1.1, we're going to be applying those concepts, building on them. It's going to take a lot of practice. Don't worry if it feels overwhelming. The more you try, the more practice you do, the easier it will get. So let's talk about pure substances. They're elements and compounds that have a fixed composition. So, meaning that a sample of water will always have 1 atom of oxygen and 2 atoms of hydrogen. Table sugar, which is sucrose, will always have the ratio of 12 carbons to 22 hydrogens to 11 oxygens. So for example, here we have NO2, we have 1 nitrogen for every 2 oxygens. So that's an elemental composition. Here we have 2 hydrogens for every 1 oxygen. That's not a 10, that's a 1. And then here we have 1 sodium for every 1 chlorine. And we have 2 nitrogens for every 4 oxygens. Now the other way we can say it, we can have 2 atoms of hydrogen for every 1 atom of oxygen, say here in H2O. Same with moles. For every 2 moles of hydrogen, I have 1 mole of oxygen, right? Because if I were to take a mole of that substance, I'd always have 2 to 1. So a lot of times we'll use that as our mole ratio as well, and you'll see why we need that later. So how do we determine the percent composition of a pure substance? Well, we know the elemental composition of each one, so you're going to find the percent. Well, here are the steps. The first thing you're going to do is find the total mass of each element. Then you're going to sum the mass of each to find the total mass of the entire element. And then you're going to divide the mass of each element, so each mass that element contributes, by the total mass of the element. And then you're going to multiply 100 to find the percent. So if I look on my periodic table, and again, I'm going to go up to my periodic table to find the mass of each one. Remember, 1 mole of a substance has the mass from the periodic table. So the first thing I'm going to do is I have 12 carbons, I have 22 hydrogens, I have 11 oxygens, and remember from the 1.1 we actually found the mass of this, but we can do it again. So if I go up on the periodic table, I see that carbon has a mass of 12.01, oxygen of 16, and hydrogen of 1.008. So I take the number of each one and I multiply by its mass. And here I get 144.13. And here I get 22.176 and 176.00. And I'm going to add that all together to find my total mass of this whole thing, right? And if I add it all together, I get 342.31. So that's the total mass if I'm adding all of these. Okay, so that I add them together and that gives me that number. Now what I need to do is find the percent of each. So for carbon, I know that carbon is 144.13 grams over the total mass, which is this down here, 342.31, and that gives me 0.421 is the ratio that is carbons. So I'm going to do the same for the other two, dividing by the total mass. Oops, 342.31 and 176 divided by 342.31. And if I plug those into my calculator, I get 0.065 and 0.514. Now I have to take these values and multiply them by 100 to put them in percent form. And then I get 42.1% of this sucrose is carbon. I get 6.5% of sucrose is hydrogen, and 51.4% of sucrose is oxygen. Okay, so now it's your turn. Find the percent composition of iron 2 sulfate, okay, and see if you can figure out the percent of each. Pause this video. So first thing I have to do is find how many of each of the elements I have. I have iron here, and I have a sulfur, and my little subscript says I have oxygen. Oop. Let's get this. Okay, so how many irons do I have? I have one. I have one sulfur, and my subscript on oxygen says I have 4. I go to my periodic table and look up their masses. So iron is up here. Iron is 55.85, sulfur is 32.06, and oxygen is 16. And I'm going to multiply by how many of each I have. So iron is 55.85, sulfur is 32.06, and oxygen is 16.00. And when I multiply them, I get 55.85, 32.06, and 64.00. Now I'm going to add those numbers together. If I add those together, I get the mass of the whole compound, which is 151.91. And I'm going to take that number to find the percent of each, or the ratio of each. So I'm going to divide each one by my total mass. Divide. And then I have to multiply that by 100 to put it in percent form. And when I do that, I get 36.8% of iron, I get 21.1% of sulfur, and I get 42.1% of oxygen. So hopefully that was easy for you. Now let's move on to how to use this composition of a pure element to find the empirical formula. Well, what's the difference between a molecular and an empirical formula? A molecular formula is the actual number of each atom in the compound. So for example, up here in sucrose, we have 12 carbon, we have 22 hydrogen, and 11 oxygens. The empirical formula is the smallest number of atoms of each element in a compound. So again, that you would simplify your formula to the lowest number. So what does that mean? If I had, say, C2H4O2, I would have to simplify that. That would be my molecular formula. But my empirical formula is actually CH2O, because that's the simplest form, or the simplest ratio of the atoms in that element. Okay? So we have this nice little phrase that you can use to remember to go from the percent composition to the empirical formula of a sample. You want to percent to mass, then take the mass and convert to moles, divide by small, and then multiply till whole. So what does that mean? Let's practice. Percent to mass, mass to moles, divide by small, multiply till whole. So here's an example. A compound was analyzed and found to contain 13.5% calcium, 10.8% oxygen, and 0.675 hydrogen. What is the empirical formula of the compound? So the first thing we do is we change our percent to mass, then we convert the mass to moles, then we divide by the smallest number of all of our 3 answers here, and then we multiply it till we find a whole number that they all go into. Okay? So the first thing we're going to do is convert our mass, our percent to mass. So we have 13.5% calcium, we have 10.8% oxygen, and 0.0675% hydrogen. To convert that to moles, anytime you have a percent, remember, we can use a percent and we can go straight to grams. So if we have a percent of something, we can go ahead and turn that into grams. So we have 13.5 grams, and we have 10.8 grams, and we have 6.75 or 0.675 grams. Okay. So how do we go from grams to moles or mass? Yeah, grams to moles. Well, we have to use the molar mass. So here we go. We want to get rid of grams, so grams has to go on the bottom. We know we convert into 1 mole. That's the molar mass. So grams on the bottom. For every 1 mole, we have a certain amount of grams, and that we read off the periodic table. So again, we know that calcium, if I go to my periodic table up here, I know that calcium, for 1, the mass is 40.08. For oxygen, it's 16, and for hydrogen, it's 1.008. So I'm going to plug those numbers in. Calcium is 40.08 grams. My grams cancel out, and I'm left with moles of calcium. Okay, and then I do the same for oxygen, which is 16.00, and hydrogen is 1.008 grams. Again, my grams cancel out. I'm left with moles of each one, and I get 0.337 moles of calcium, 0.675 moles of oxygen, and 0.670 moles of hydrogen. So that's the ratio, the mole ratio of each of my elements in my compound. Now, how do I figure out the formula, the empirical formula? Well, it says divide by the smallest here. Divide by small. So my smallest number is 0.377. So I'm going to divide each one by 0.337, 0.337, and 0.337. And I get 1 calcium for every 2 oxygens and 2 hydrogens. Now, this part that says multiply till whole, we don't have to do that because we got 1, 2, and 2. So we already have whole numbers here. When you would multiply to whole, it would be like if you had 1.5. Say one of these numbers came out to 1.5. You would have to multiply each of the values, each of these values, if it was 1.5, by 2 to get a whole number. So anytime you multiply one thing, you have to do it to everything. So my empirical formula for this is 1 calcium for 2 oxygens and 2 hydrogens. Now, it actually looks like this, and we'll learn about this later because this is a ionic compound. But OH is a polyatomic ion, and so this is the correct way to write the empirical formula. But if you wrote this, that would be okay too. You probably would get credit for it. This is just telling you how to multiply till whole. So if you get 0.5, you're going to multiply each of your answers by 2. If you get 0.33, you're going to multiply each of your answers by 3. And if you get a number that says 0.25, you're going to multiply each of your answers by 4, okay? So when you practice, and if you get a number that ends in one of these, you have to take the answers for all of your elements and multiply them by these factors to get a whole number. Okay. So we're moving on. That was how to find the empirical formula of something. Now we're going to talk about using hydrates, or what we call gravimetric analysis, to determine the empirical formula of an element, or of a hydrate specifically. So a hydrate is a substance that attracts and absorbs water. An example, so water. An example is iron 3 chloride hexahydrate. In this substance, there are 6 moles of water present for each 1 mole of iron 3 chloride. The amount of water present per mole of substance can be experimentally determined by heating the hydrate, the hydrated substance until all the water is released, or when the mass final remains constant, or the final mass remains constant. Then the moles of the water and the moles of the anhydrate, so an anhydrate is a substance without water, can be calculated. So this is a lab that we do for AP Chem, so we will be doing this lab, but this is how you take the data from the lab. So it says a student is assigned the task of determining the moles of water in 1 mole of MgCl2 in H2O. The student collects the data shown below. And so we're going to try to find what this N is, okay? We're going to try to find how many moles of water of this hydrate are in this formula. So the theory behind this is if we heat the substance, all the mass that is lost is water. So we're going to heat it until the water evaporates off, and all we are left with is the MgCl2 substance. So the first thing you have is the mass of your empty crucible. So that's the device that you're going to put your hydrate in. And then you have the initial mass of the sample plus the crucible, okay? Finally, you're going to start heating that as the water evaporates off until you have no change in mass, okay? So you're looking for a steady change, kind of where the mass stays constant, and that means all the water has evaporated off, and then you're just left with your MgCl2. Is we're going to calculate how much of the mass of the water was lost. So how do we figure that out? Well, we look to where the mass stayed constant. So right here, you could use either of these numbers, but we're just going to use this last number. And we're going to minus it from the mass of our initial sample. So we have 25.825 grams initially. And after we heat it, we have 23.977 grams, which gives us 1.848 grams. And we know that that's water because the loss in mass has to be the water. Then we're going to convert the grams of water to moles. Okay, so how do we do that? Well, first we have to find the molar mass of water. So we know that water has 2 hydrogens and 1 oxygen, and we multiply that from our periodic table values. Okay, so I got those values, and if I add that together, I get total 18.02 grams of water in 1 mole. Okay, so now I'm going to take 1.848 grams of H2O. That's what I found how much water I lost. I put that over 1. I want to get rid of grams of water for every 1 mole. That's my molar mass that I just calculated above. And I get 0.1026 moles of water that I lost. So that's how many moles of water were in my sample. Now, I'm going to find out how much of my anhydrate that I had. So again, I'm going to take my mass of my final amount, and I'm going to minus the mass of the container it was in, the crucible. So that's 23.977 grams minus 22.347 grams. And that is 1.630 grams, and we know that has to be the MgCl2 because the water is gone. And now that I have grams of MgCl2, I want to convert that to moles. So over here, I'm going to start with what I'm given, which is 1.630 grams of MgCl2. And I'm going to put that over 1. I want to get rid of grams of MgCl2, MgCl2 over 1 mole. And how do I find how many grams are in a mole? Well, I have to find the molar mass. So I know I have magnesium, I have 1, and chlorine, I have 2. And I multiply those by their molar mass on the periodic table. And so if I go up here and I look up Mg, it's 24.3, and Cl is 35.45. And then I multiply them, add them together, and I would get 95.21 grams. I'm going to plug that number in here, 95.21 grams. So I multiply, my grams cancel out. I'm left with moles, so I take 1.630, multiply by 1, divide by 95.21, and that gives me 0.01722 moles of MgCl2. Now this is similar to what we did above. We found the moles of water right here, and we found the moles of magnesium chloride here. And so remember, to find the empirical formula, we had to convert our mass to moles, and now we divide by small. So I'm going to find that smallest number, which is 0.01722. So I'm going to divide my water, 0.1026 moles of H2O, by 0.01722 moles. And if I can do the same here for my moles of MgCl2, but we know that's just going to be 1, right? So that's 1. And this is 6, or approximately 6, if I round to 6. So that means there's 6 moles of water for every 1 MgCl2. So I found my N value right here. So my final hydrate is MgCl2. I put a little dot there for my hydrate for 6 waters. And that is my final answer. Okay. That was a lot, right? Well, we have one more thing to do. And this is pretty advanced, I'd say, for some students. So we can do something called a combustion analysis. And if you had chemistry before, you know what a combustion reaction is. And we'll learn more about combustion reactions in later units as well. But a combustion reaction is just a hydrocarbon. So a hydrocarbon is this here. It's a hydrocarbon, and this is a one form of a combustion reaction but it's common on AP, plus oxygen, and the products are carbon dioxide and water. Okay, so it's any hydrocarbon that reacts with oxygen gas to give us carbon dioxide and water. That's a combustion reaction. Now, you don't need to write that out for this type of problem, but just some context so you understand what's going on in the chemical reaction, so you know why we can use certain values to determine our moles. Okay, so in order to find the empirical formula, or the formula of the hydrocarbon, you're going to have to convert the grams of the products into moles. So the first thing you're going to do is you're going to find the moles of CO2. And it tells you you have 22 grams of CO2. And we know we can find the mass of carbon in that because the only products are carbon dioxide and water. And so that means all the carbon is in the carbon dioxide. So we have conservation of matter in chemistry, which means that matter cannot be created or destroyed, so it has to convert into something. So here we see that the carbon, all the carbon from this hydrocarbon here, has to go into CO2. So if we know the mass of CO2, we can find the mass of the carbon. So we have 22.0 grams of carbon . or sorry, CO2. And now we want to find how much of that is carbon, okay? Well, the first thing we have to do is we have to convert the grams of CO2 into moles of CO2. This should be review, and if it's not, it's okay, but just make sure you practice. So we have 22.0 grams of CO2. I want to get rid of grams of CO2, so I put that in the bottom. And I know for every 1 mole, so I'm going to convert this to moles of CO2, I have my molar mass, right? So for every 1 mole, I have my molar mass. So I'm going to look up and find my molar mass of CO2. Remember, carbon, I have 1, and oxygen, I have 2. If I use the periodic table, you'll see that carbon here is 12.01 and oxygen is 16. So those are the numbers I'm going to use. 12.01 and 16. And 16. So if I multiply 12 times 1 and 16 times 2, and if I add that together, I get 44.01 grams of CO2 for every 1 mole. So that's the number I'm going to put here, 44.01 grams. And that, again, is my molar mass. So if these cancel out, 1 mole of CO2, I've now found my moles of CO2, but I don't want my moles of CO2. I want carbon. Well, since I want to get rid of moles of CO2, and I'm going to erase this down here. That was just showing you how to find the molar mass. I want to get rid of moles of CO2, and this is down here, okay? And I want moles of just carbon. Well, I know that for every 1 whole thing of CO2, I have 1 carbon, right? So if I had 1 mole of CO2, I would have 1 mole of carbon. So those cancel out, and I'm left with moles of carbon. But I don't want moles of carbon, right? I want mass. I want mass of carbon. So again, I get rid of my moles of carbon by putting it on the bottom. And I want my grams of carbon. And how do I go from moles to grams? Well, I have to use the molar mass of the periodic table. So for every 1 mole of carbon, as before, we found that I have 12.01 grams of carbon. So now my moles of carbon cancels out, and I'm left with grams. I multiply everything on top and divide by everything on the bottom. So 22 divided by 44.01 times 12, and again, I'm ignoring the ones because they don't change my math. I get 6 grams of carbon. Okay? So now I have to do the same thing for hydrogen, H2O. And again, I know that all my hydrogen, because of the conservation of matter, is in this water because there's no hydrogen in CO2. So I know all my hydrogen came from the transferred into this water. So I can find that by knowing the mass of my water, similarly how I did with carbon dioxide. So the first thing I'm going to do is I'm going to convert my grams of water to moles. I'm going to put a 1 here. I start with what I'm given. I want to get rid of grams of water, and I want moles of water. And that I have to do my molar mass. So every 1 mole of water, I look to my periodic table. I have 2 hydrogens times 1.008. I have 1 oxygen times 16. If I add that together, and again, these values are coming from my periodic table, I get 18.02 grams. So I'm going to put that in here, 18.02 grams for every 1 mole of water. That cancels out, and if I were to if I were to divide 13.5 divided by 18.02, I would have moles of water. But I don't want moles of water, so this is in my numerator, so I want to get rid of it. I put moles of water in my denominator. I want moles of hydrogen. Okay, so let's pay attention to this. So I'm getting rid of my moles of hydrogen. If I have 1 whole mole of water, for every 1 mole of water, I actually have 2 hydrogen, right? So for every 1 water, I have 2 hydrogen. So I actually have to put a 2 here, or 2 moles of hydrogen. So my moles of water cancel out, and I'm left with moles of hydrogen, but I want grams of hydrogen. So I have to put moles of hydrogen on the bottom to cancel those out, and I know my molar mass can give me grams of hydrogen. So for every 1 mole of hydrogen, if I look on my periodic table, I will see that there's 1.008 grams. That's my molar mass. And that'll give me my grams. So I'm going to take 13.5, divide by 18.02, multiply by 2, and then multiply by 1.008. And that will give me 1.51 grams of hydrogen. So now I know my grams of carbon, my grams of hydrogen, and finally, I can find the mass of my oxygen in my sample. Now, oxygen is in both my products, so it's in CO2 and H2O, so I couldn't take the masses of those and find out how much mass of oxygen I have. But there's conservation of mass, so I know that my mass of my carbon and my mass of my hydrogen have to add up to the mass of my total hydrocarbon that I started with, okay? So if I have 11.5 grams of my hydrocarbon, and I minus that from the mass of the carbon that I found, which was 6 here, plus, oops, that's going to go away, plus the mass of my hydrogen, well, I know the rest of it has to be oxygen. So that gives me that the remainder of my hydrocarbon was 4 grams of oxygen. And oxygen is O2 because it's oxygen. 4 grams of oxygen. We'll just leave it O, okay? Because that's the oxygen from our hydrocarbon. Okay, so now we have to determine the empirical formula. So now we have to convert it back to moles because the moles give us the ratio of everything. So we want the empirical formula of our hydrocarbon up here. So we want the empirical formula of this. So I got to convert everything back into moles. I have 6 grams of carbon. I have 1.51 grams of hydrogen. And I have 4 grams of oxygen. In order to convert it back to moles, I have to divide by its molar mass. So I'm going to divide by the molar mass of each. I get 1 mole. And if I look on my periodic table, I see that 1 mole of carbon is 12.01 grams. We know that 1 mole of hydrogen is 1.008 grams. And 1 mole of oxygen is 16.00 grams. Okay, and remember the grams cancel out. I'm left with moles of each. And if I do that, I get 2 carbon, I get 6 hydrogen, and I get 1 oxygen. So we would divide by small, which is 1, so the numbers don't change. So our empirical formula is C2 carbons, H6, so 6 hydrogens, and 1 oxygen. And that is your answer. Whew, that was a lot of information. Again, make sure you practice these problems. They all are a little bit different, similar concepts. And again, make sure you understand how to convert from moles convert to moles using the molar mass. And good luck.